All right, welcome to problem 6.5. This is in Smith Van Ness, 8th edition. We're in the 6th chapter, problem number 5 at the end of the chapter. Problem statement says a pure fluid is described by the canonical equation of state G is equal to gamma plus RT log of P, where gamma is a function of temperature. They want us to determine for such a fluid expressions for volume, entropy, enthalpy, internal energy, and heat capacity, Cp and Cv. And then they ask us, what kind of fluid is this a good model of? This is an important model of gas phase behavior. What is it? So ideal gas, what kind of a real gas? That's what they want us to figure out. So anyway, in approaching this problem, what this problem is trying to illustrate is that the Gibbs energy, remember the Gibbs free energy, we said was a generating function. So if you go back and look in your notes, look at that section. This is covered on pages 219 to 220. That's a lot of why we spent all that time driving the fundamental property relations and the Maxwell equations so that we could get to this Gibbs energy and show that once you know the Gibbs energy, then you pretty much know everything else about this fluid. So that's what we can start with. All right. So if we go to page 219 and 220, we see equation 6.38 gives us the equation for volume. All right. So the equation for volume says that V over RT is equal to partial of G over RT with respect to pressure. All right. And that's going to be at constant temperature. So this is how Gibbs free energy or Gibbs energy is a generating function that allows us to calculate the volume. Now, we need to get our equation of state, all right? Remember, back in our notes, we divided everything through by RT to make G dimensionless, or to make that term dimensionless. So we can do that here, all right? So our equation of state, and I'll keep it up here, G over RT, all I'm going to do is take this equation and just divide everything left and right side by RT. So G over RT is equal to gamma over RT, all right, plus RT log of P divided by RT is natural log of P. So this is our equation of state that we're going to use throughout this problem, all right? So once we know that, then we can go and now let's figure out how we solve for the volume. Well, I'm taking the derivative of this term with respect to pressure, all right? So that means I take the derivative of this term with respect to pressure and that term, second term with respect to pressure. Gamma is a function of temperature only. R is our ideal gas constant. That's a constant. T is temperature. There's no pressure dependence in this term. So the derivative of that with respect to pressure, that first term is 0. All right. And then what do we have? Oh, I should partial G over RT. Make sure we keep straight what we're doing. So that's equal to that, and then plus the derivative natural log of P. That's just 1 over P. All right. So what we have now is V over RT is equal to 1 over P. All right. And we can rearrange this several different ways. We can say PV over RT is equal to 1, or PV equals RT. All right. Or if we want to solve for pressure, V is equal to RT. Sorry, for volume, V is equal to RT over P. All right. And that, of course, is ideal gas model. All right. And so that is the answer to this question. Hopefully everything else we're going to get in this derivation is going to be consistent with an ideal gas, what we've seen in chapters 3 and 5 as well. All right. So that's how we solve for the volume. All right. The next, what we're asked to solve for is the enthalpy. All right. So the enthalpy, we can look at equation 639. All right. That equation says that enthalpy over RT is equal to minus T times partial derivative of G over RT with respect to now temperature, and that is all at constant pressure. All right. So what we're going to have to do then is take the derivative of this equation of state now with respect to temperature. So as you can probably see right away, this term, the derivative of this with respect to temperature at constant pressure is 0. So all we have to worry about is this term over here. So what I'm going to do is first I'm going to start over here and I'm going to write H over RT, and I'm going to move this temperature over here. So that's going to be RT squared. All right, is going to equal to partial of G over RT with respect to temperature. This is at constant pressure. And so this is going to equal to partial of what? That will be gamma over RT plus natural log of P with respect to temperature at constant pressure. All right, and we already mentioned that this term is going to go to 0. All right, so what we're left with then is partial of gamma over RT with respect to temperature. All right, and I forgot the minus sign. Make sure you keep the minus sign in. All right. All right, so we can then do our derivatization, but first remember that R is a constant. Let's just pull that out. All right. So H over, pull that out, and so then we're left with partial of gamma over T with respect to temperature. All right. And we need to make sure we keep forgetting that minus sign. Make sure you keep that minus sign in. All right, so gamma is a function of temperature. T, of course, is a function of temperature. And so what we've got here is we've got a case where we need to use the quotient rule back from either Calc 1 or Calc 2. Remember that said if we have F prime over G prime, that's equal to what? That's equal to F prime, the way I have it written down, F prime times G minus F times G prime divided by G squared. All right? And so F, in this case, is gamma, right? And G is temperature. So this is equal to minus 1 over R times, now let's do this, all right? So this is F prime, which is partial of gamma with respect to temperature. That's a big bracket here, all right? Times G, which is temperature, all right? Minus F, which is gamma, times G prime. G prime is dt dt, all right? And that's just equal to 1. And then, don't forget our denominator, that's T squared. All right? So that's what we've got. All right? And remember, this is H over RT squared. All right? So what can we do? Well, we can now start to simplify. We can cancel the R's. All right? T squares cancel, and so what we're left with is H is equal to, this will be, now remember we've got this minus sign, so minus a minus, this will be gamma, all right, which is in your book uses that it's a function of T, all right, and then minus, because this is minus a positive, minus T times d gamma dt. All right. That's our equation for enthalpy of this gas. All right. Does this look like an ideal gas? Heck if I know. All right. We aren't given the formula gamma, but what we'll find, hopefully it is, all right, and what we'll find is that once we do some more calculations, we'll see that yes, indeed, this is consistent with an ideal gas model. Notice that enthalpy is a function, it appears it's a function of temperature. All right, next part, we want to calculate entropy. All right, we want to calculate entropy. So we go to page 220. I don't think your book has an equation number, but the entropy calculation is just S over R is equal to H over RT, all right, minus G over RT. So the nice thing about this calculation is we don't have to do any more partial derivatives, all right? Thank goodness. We've already done all the partial derivatives, and so we can just plug in and we can solve for that. We calculated H just on the previous page, so gamma as a function of T minus T times d gamma dt. All right, and that's H, and then we divide through by RT. All right, and then minus G over RT. What is G over RT? So that's gamma over RT, all right, plus natural log of P. We don't even have to do any derivation of that because that is our equation of state that we have there, all right? And so what we're left then with is just to simplify this, and so we get S over R is equal to minus, so do some simplification there, so that's minus T over RT, all right, times partial of gamma with respect to temperature, and then that's just minus natural log of P. So we've got gamma over RT. If I skipped a couple steps, I've got gamma over RT minus gamma over RT. That cancels out. So all we're left with is this term right here, minus T times d gamma dt, and that's divided by RT. All right, and then if we want, we can multiply through by R, and so we're left with S is equal to minus d gamma dt, all right, minus, and then multiply through, that's minus R natural log of P. All right, that is our equation for enthalpy. All right. Next step is we can calculate internal energy. So calculate internal energy, and there's a couple things you can use. Equation again, U over RT is equal to, this is just H equals U plus PV, rearrange, H over RT minus PV over RT. All right, so that's how we calculate internal energy. Now, one of the things is we already know from the previous calculation that we did on volume that this is an ideal gas, right? And so it'd be tempting to just say, oh, this is an ideal gas, PV over RT, that's equal to 1. Well, that's not really how we're supposed to do it. It'd be better if we just if we go ahead, because we don't know that it's an ideal gas, so it'd be better if we went through and actually did the calculation to prove that is how it works. So anyway, so U over RT is equal to H over RT. What is H over RT? H is gamma minus d gamma dt times T, all right? Make sure I got that copied right from the previous page. Yes, I do. And so that is divided by RT. All right. And what is PV over RT? All right. And so we take minus so we've got P. What was V that we calculated before? Well, we calculated V before. That's equal to RT over P. All right. And that's divided by RT. All right. So this is a little pedantic. You may think I'm picking at nits here, but we really need to take the equation that we derived from volume from the previous page and put that in here. And as you'll see, this all goes to 1. All right. And so U over RT is equal to, we can say, gamma over RT minus d gamma dt, and then we've got these t's cancel out, so that's 1 over r, all right, and then minus 1. All right. And so if we want to multiply through by RT, internal energy is a function of gamma, so this RT is going to cancel out. This will be minus, and my gammas are not perfect every time. Hopefully you can figure that out. The R is going to cancel, be left with T, and then minus RT. That's our equation for internal energy. All right, so the next part of the problem, we want to calculate the heat capacity, C sub P. All right, well, how do we do that? Well, this is where we've got to remember what we had back in chapter 2, or maybe it was chapter 3. C sub P is equal to what? Partial of enthalpy with respect to temperature at constant pressure. All right. So what we're going to have to do is we're going to have to go back and we're going to have to calculate we'll get our enthalpy term. So if I can find that. Enthalpy is equal to gamma, all right, minus d gamma dt times T. All right. So we take the partial derivative of that with respect to temperature. So the derivative of the first term, that's just gamma with respect to T. And we can write the constant pressure, but I'm going to skip that because pressure is constant. All right. Now what we have here is we have the product rule. All right. So you've got UdV plus VdU. All right. And so this will be minus U times what's dV? That's dt dt, all right, which is going to be 1. All right, and then plus, now you've got this minus sign here, so that's minus T times the derivative of that with respect to temperature, and so that's just going to be the second derivative of gamma with respect to temperature. All right, so simplify d gamma dt, d gamma dt, those things are going to cancel out, and we are left with minus T times the second derivative of gamma with respect to temperature. That is our constant pressure heat capacity. Does that look like what we have for an ideal gas? Again, right now we don't know what gamma is, so just if you didn't know any better, who knows? All right, so don't worry about if it doesn't look. This is, again, sometimes in thermo you just got to trust the math. You got to trust that you're doing it right. All right. So the last part is we want to calculate C sub V. All right. And one of the things you could say is, well, you know, we know it's an ideal gas, so let's just take the shortcut. Let's say that we know for ideal gases that Cp plus Cv is equal to R. So we can just say that Cv is equal to Cp minus R. Again, technically, we don't know. We're supposed to work this problem like we don't know it's an ideal gas. So what we have to do then is we have to go back and we have to look at the definition of constant volume heat capacity from chapter, again, I think it's chapter 2 or 3, and that is the partial derivative of internal energy with respect to T. All right. So what do we have to do? We have to go back and we have to dig through what is internal energy. Go look up a couple pages. Internal energy was gamma minus T times d gamma dt, all right, minus RT, all right. So we take the derivative of that with respect to temperature at constant volume. So that is partial of gamma with respect to T. All right. And now, again, we have our product rule that we have to take into place. So it's minus T times second derivative of gamma with respect to T minus gamma dt times dt dt is 1. And then minus, we take the derivative of that with respect to R, and what do we, or with respect to T, minus RT, that's minus R. All right. So let's see, so this term and that term will cancel. And so what we're left with is minus T times second derivative of temperature, sorry, gamma, this is a gamma, with respect to temperature, all right, and minus R. So this is what Cv is. Does that make sense? Well, here we can figure out, yeah, there's something here that makes sense because Cp, this is just Cp, all right? So this is C sub P minus R. And that's equal to Cv for an ideal gas. So there we have it. We have used the Gibbs Energy as a generating function, and we've calculated all these wonderful thermodynamic properties of this particular fluid. We started with volume, took the derivative with respect to pressure. That was a pretty easy derivative. This is what we got. We then went to the next one, enthalpy, all right? It's a little more complex of a calculation because we had to use a quotient rule. So that's something that we just got to remember from our freshman, sophomore, whatever, high school years. A little bit more algebra involved, but this is what we got for the enthalpy. All right. Then to calculate entropy, all right, we just had to take what we had before, H over RT, G over RT, put it together, add them together, and this is what we got. Internal energy, very analogous method to get internal energy. If you look at this equation for enthalpy, you'll see this is reminiscent. Remember, this is minus C sub P dt over T minus R log P. There's some familiarity with what we had in chapter 5. This really doesn't look like anything we had in chapter 3. All right. But then C sub P, we just use these very simple definitions for C sub P and C sub V. All right. And again, you plug in what you had for enthalpy, you plug in what you had for internal energy, and here we finally see that now we get something that we have seen before, that for an ideal gas, Cv plus Cp is equal to R. So that is problem 6.5. If you have any questions, enter them in the discussion so that everyone can see your questions. Don't worry about asking dumb questions. There's no such thing as a dumb question, especially when it comes to thermo. And that way I can answer questions for everybody. Thank you.